Hello and welcome back to another episode of the Oxford Online Maths Club. My name's James and today I'm joined by Zakkai.
Hello.
Great to have you with us, Zakkai. This is the
Yeah.
dream for the Maths Club that we get current students on. Zakkai is a current student at New College. What are you studying, Zakkai?
Yeah. I'm in my fourth year studying maths and philosophy. So I've been doing that for 4 years now.
Brilliant. I think I first met Zakkai, oh gosh, did I meet you a couple of years ago on some sort of outreach event, maybe? We were doing some telling
Maybe
people about
I
maths or
was helping
something.
out. I was helping out in first year. I don't know if you were doing outreach stuff then,
You've been
but
here
I
longer
think
than
you
me,
were.
possibly. We're also joined by Bobby, who's moderating chat. Hi, Bobby, in chat as well. And joined by you, watching live from around the world. Hello to everyone in chat. You should let us know, obviously, if we're having any tech trouble. One time I had a guest on and I completely forgot to go live because I was so excited I was talking to my guest. And another time I forgot to unmute the guest. So I'm really sorry, Zakkai, if you have to say your intro again. They will let us know in chat if I've forgotten to
All right.
unmute. I'm going to give them a second to catch up. They're responding to something you said, so I
Okay.
think we're communicating with communicating
As
with
well.
mathematicians. Something Zakkai just said made me really smile, which is before we went live, we had about 1.5 minutes before going live, and I said, Zakkai, okay, we're going to go live in a couple of minutes, and Zakkai said, okay, I think I'm going to do some maths then. Just trying to do some
I
maths in
yeah.
between. Miles
Uh,
asks, what do you think of the
I'm.
course, Maths and Philosophy? Um,
Oh yeah, I love it. It's the perfect course, and I think everyone should take it if they are interested in both subjects. I didn't know what I was going to take until I found out that this subject existed, and then I knew that this is exactly what I was going to take. Um, and I've done the very stereotypical route of going like towards the middle of both. Kind of the intersection is now what I study, which is hopefully a little bit of what I'm going to talk about later.
so just for people who don't know, Oxford does this course in Maths and Philosophy. What is that middle bit? What's the overlap between Maths and Philosophy?
I mean, there's a bunch of places you could go with it. The most obvious ones are philosophy of maths, and also like logic. There's a lot of logic, and there's mathematical logic and philosophical logic, and they have their differences, but the root is the same. I'm kind of studying both now. Set theory also kind of comes out of that. And this is like the kind of studying of infinity, and uh, on the one hand, studying of infinity, and on the other hand, like thinking about what base assumptions we have when we use maths, and like what the foundations of maths are. It's kind of yeah. So that's kind of where I research. I also study a lot of history of maths. Yeah, but that's for another day maybe.
Another day, maybe. Um, hey, somebody in chat's come at us with they know that New College was founded at the same time as Winchester College, and I think they're throwing that at us in chat like it's a bad thing. But New College in Oxford is like
Yeah,
it's
there
got
is
some
like a
more.
historical link between the two. I think it was founded by the same person. That link's ended a few hundred years ago. It's the same. King's College Cambridge has a historical link with Eton. They were both founded by the same person as well. It's like this is a thing that happened in the 1300s, I guess.
I found out recently
But
that Winchester College in Winchester was founded as a college for the poor to do teaching
oh,
there, which is quite different. Oh, Kai wants to ask you a question from last week, which I fumbled badly. Please, Zakkai, please do not watch the recording of last week and me fumbling this question. The question they asked me last time was, what is maths the study of? You know how physics is the study of the real world and chemistry is the study of chemicals. What's maths the
sure.
study of?
I think maths is too broad to have one short question for that. In my head, like the act of doing mathematics is going from kind of looking at a bunch of things and being like, okay, what can we get to from there? Like, if we assume all of these things, what can we reach? Or the vice versa, like, how do we reach this thing from these assumptions? Um, it's kind of, yeah, this process of like thinking like, I want to prove this, but I only have these things to be able to prove this by. I think what is math to study? It's like the study of math. It's kind of I don't want to. It's a circular definition, but like I study like self-referential functions, so I think that's fine. Um, because like any type of math will be the study of something else, right? I want to go on and study like do the study of infinity or the study of blah blah blah. Whereas someone who does applied maths, I don't touch that stuff, but it's very different. Um,
We're quite different mathematicians in a way. I think we don't have any maths in common in
yeah,
a way. We
I
have this
remember
kind of common
I said
language.
at I remember I said at one point how I was taking a course in model theory, which is a branch of logic that is usually applied to algebra, which algebra is a branch of pure mathematics. And I saw that and was like, oh, that's too applied for me. And I think you just rolled your eyes and walked away, kind of, at the
Sorry.
prospect of algebra being applied.
Yeah. Other people watching will be on my side, I'm sure. No, I shouldn't try. I shouldn't try and get people to say sides. Arjun in
Maths and
chat.
philosophy, it's very pure mathematical. So
I want to
I
read this
think
quote from
it makes
chat
sense.
because Arjun, I think, has outdone both of us by. They've answered the question. They've said that maths is the study of the absolute truth and the journey of problem solving, which I think is quite poetic. It's just quite a nice thing.
Yeah, I think absolute truth is an interesting. I think it. I don't know. You could truth with reference to what? I mean, this is kind of my because a lot of logic is studying like this thing is true when you're talking in this because like some things are true in some like realms but not true in others. This is kind of my philosophical thing. There is a really deep philosophical question about what is absolute truth. But a fun thing with maths is that we can't talk about truth within mathematics. Like if we were writing maths in the language of maths, we can't talk about truth without paradox. And that's not what I'm talking about today because that's getting to that is very complicated.
Chat's,
But
lead, chat's leading one thing to another. I think I should clarify just in case. Zakkai, I think, can't see chat. I can see, even though it's right
no, no,
underneath them.
I can see a blurry like I can see the screen you can all see, but kind of at a much lower resolution.
So
So I have no
Zakkai,
idea.
you don't know that you were just leading towards Gödel's incompleteness theorem
Oh
at
yeah,
exactly the moment that someone in chat asked, "Do you do Gödel's incompleteness theorem at Oxford?" Which is just
I
beautiful.
am currently studying a course called Gödel's Incompleteness Theorems.
A course called
And I
God.
also studied it as part of my philosophy of maths course, just from a different perspective.
Sorry to make you repeat that. That's a
So,
course that's 16 lectures or something, or
yes, 16 lectures, and there's like 4 classes, problem sheets,
four
what
classes, a
have
problem
you.
sheet, and an exam on Gödel's incompleteness theorems plural. Yeah,
Plural. Yeah, there's
yeah,
two.
that's probably the best possible answer you could give to "Do you do X?" Yeah, we do the plural of X
And
over the course of 16
yeah, yeah,
lectures.
yeah. And also, we also study both of them from a different
Right.
perspective in a different course. So.
I'm aware that's very annoying for everyone in chat because we haven't said what Gödel's incompleteness theorem is. I would encourage people to Google it, and I might put a link in the further reading. Okay, also on screen is an advert about promised summer schools, and I have to do the poll because we like to start with the poll of how was your day, which is a tradition. I don't know if you've seen us do this, Zakkai. We like to ask how was your day today, and
That's
we
very
also
true.
like to turn on the results so that people can see how people's day were.
I
How
do remember.
people's
Oh,
days.
I forgot when I introduced. I use they them pronouns, by the way.
Oh
That's
yeah, sorry.
something I realized I forgot. Um,
Um,
just for more about me.
yeah,
This is good. I'm seeing a lot of bars on the right hand side of the screen. I assume that is that the good part of the
that's the
day?
good part of the screen. We're
Okay.
looking at people having a 4-star or a 5-star day, and who have turned up to find out about Infinity. And also, I'm always looking at people with a 1-star or a 2-star day because I think that they're having a bad day and they've logged in to see
Mm.
some mathematics, which is it's a
I
combination.
decided to wear
It's
my
a
maths
choice.
earrings as well for this.
Oh yeah, they're
I've
really
got
small on screen,
the
which
knots
is
maybe are
fine
less
for me.
exciting, but I've got these little Klein bottles.
I haven't got a view. I want
Um,
to. I want to switch to your camera. That's lovely.
yeah, I don't know, but there's a very cool. Actually, one of my course mates studying maths here gave these to me. I was like, oh,
That's
gift,
brilliant.
very sweet.
I am
Hmm.
wearing my incredibly cool headset so that I can hear what Zakkai's saying. 2 stars to somebody in chat because both my maths lessons were cancelled today, so that's
Oh,
bad times. And Akai would like to know how your day's going, Zakkai, on a scale from 1 to 5.
yeah. 4. It would be a 5 if I was able to solve that question I was trying to solve earlier.
Oh yeah, I only gave you sort of 2 minutes
Um,
before we went live to try and finish off
well, I was working on it, but for about an hour before I joined the call. So
um, so Promise Summer School, because I've got it on screen, is an opportunity. It's hosted in Oxford and it's a math school for pre-university students. I think that's the requirement that you have to be over 16 but under, you haven't not started at university. There are applications for that. I've been meaning to show you this advert for a couple of weeks. I'm sorry that I forgot to show you this advert. It's been in the Miro board for a couple of weeks. If you watch the previous episodes in freeze frame, you can see the corners of it as I zip around it, forgetting to show it to you. That's not really interesting so much as, that's just one of those things. How do I get back to showing you this? There we go. Is it open for people? So I think the rule is pre-university, which Should we have a go at it? Somebody had a maths test. I don't know if they're suggesting that was a good thing or a bad thing. Spent all morning revising vectors. I guess some people have got mocks coming up as well and things like that.
If it makes you feel better, I don't remember what
Don't.
integration is, let alone vectors. So I've forgotten a lot of mathematics, but I've learned a lot of different mathematics.
There's quite a bit of chat delay, so I'm just going to quickly go through some chat, catching up on chat. There is a reaction to Klein bottle earrings in chat that I thought I should pass on to Zakkai.
No, those are very cool.
Kai has linked to a YouTube video which Kai claims is Gödel's incompleteness theorem. It would be very mean if that was actually some sort of music video.
Not mentioning which music video. I was moderating the chat the day that you got rickrolled. That was very entertaining for me.
That was a bad day. Wait, you were moderating chat? I thought the problem was that I had to moderate chat and I had to get rickrolled by the person.
Oh no, maybe I was moderating a day before that and saw the rickroll and didn't let it go through out of kindness. But then the next week you had to moderate because other people weren't available.
Okay. Should we talk them about Infinity? That's the plan for
Yes.
today, right? We're going to talk about Infinity.
Should we? Yeah.
Should we go?
I'm gonna get through as much as I can without racing ahead, and I'm sure you'll slow me down if I am. So kind of the first thing, I think, which some people in chat might have heard about before, is picture a hotel with one room for every natural number. So one room for every whole number. There's infinitely many rooms. And it's completely booked. Every single room is full. There's someone in every single room. It's completely booked. That's kind of all there is to say. Oh, thanks. This is very nice little drawing. Someone walks into the hotel, really needs a place to stay for the night, asks the usher or the receptionist, do you have any rooms available? And the receptionist looks at their, their little computer screen, type. Oh, it looks like all of our rooms are fully booked, but I think I can squeeze you in somehow. So should I ask a question for the chat, maybe? How can... I'm telling you, it is possible to get this person in, even though every single room is, busy and occupied.
Yeah, so some people in chat have reacted by saying, aha, it's Hilbert's hotel. They know I don't know if they've stayed there or something, or they've just, heard of this famous hotel.
Wow.
And people are now volunteering a solution of how to get everyone in. How to get this how to get this new person in.
Yeah. What are they saying?
So the thing is that people always put the fastest things to get typed in are the shortest. So I like to give them a moment to type longer answers. Or in case there's somebody who's typing a longer answer in chat, and then you tend to get longer sentences if you leave it a second. But several people have said, aha, maybe they've heard of Hilbert's Hotel before.
I'm having to really restrain myself from talking about history and talking about Hilbert as a person, because he was very interesting. But I'm gonna
quickly. In your opinion, good person, bad person? Should we rename Hilbert?
Good person. Good person.
Okay.
Actually, good person. There were other people at the time who he had huge confrontations with, who did describe themselves as Nazis, and so very much was good person in hindsight, and was a huge feminist. Really helped Emmy Noether with her work and anyway, I'll get carried away.
I shouldn't start you on history. We might do a separate episode on history.
My laptop is currently balanced on a stack of history books.
Sorry, I'm just trying to encourage some engagement in chat. Do people want a history episode? Sorry, just trying to pump my numbers. I try to get that. Ooh, some sort of poll. So Miles is disappointed because Miles has seen this before. We've got a couple of joke answers as well. Kai suggested that this person can go and sleep in the stables, which is...
Oh, yeah. Well, I assume that would be numbered as one of the rooms, which is the problem, because that would be booked. Yeah.
Lots of people have said you can move everyone down a room.
Yes. So I've talked to people before about this question, and sometimes their first instinct is, well, if there's infinitely many rooms, just stick them on the end. But the problem, of course, is that there is no end. It keeps going on forever, and there's someone booked in a room. But what the usher does is ask everyone in, like, ask the person in room one to move to room two, two to three. So everyone in room n has to move to room n plus one. And then whoop, there's no upper bound on the natural numbers, and so room one is now left open, and the new person can slot right in. So that's like a weird thing when it comes with infinity, is that you've got these weird things that shouldn't work. This is why people say infinity isn't a number, right? Because numbers feel like addition should have some kind of impact, right? Infinity plus one equals infinity. So what if you subtract infinity from both sides, you get one equals zero, which is not something you want. And of course, infinity isn't a number, but it is a type of number, and I'll get to that later. Um, let's stay with the hotel for now. Of course, if any finite number of people arrive to the hotel, say if a million people turn up to the hotel, the usher can just move everyone a million doors down, and then there'll be room for a million more people. The question is now, okay.
Before we do the next one, can I pull some things from chat really quickly? Sorry.
Yes, of course.
So someone wants, can you put them in a room halfway down? And I sort of know what they mean. Of course, halfway, going to be, the hotel's really, really long, so
yeah.
I can't really tell you which room's halfway down in the middle of the universe. But you could put them in room 100 and shuffle down the people beyond that. I think that works.
Yes. So you could instead, if you have really important guests staying in rooms 1 through 99 that you really don't want to disturb, you can instead ask everyone from 100 on to move and then slot the new person in there.
People are a bit worried about the disruption, I think, that it's getting absolutely everyone to move along.
Yeah, staying at this hotel is rough for most people. They're moving your rooms constantly.
We've already had a bad service TripAdvisor review in chat. Somebody says, is it inefficient to move everyone? And kind of, I guess, efficiency is maybe not our concern.
Yeah, I had a lecture the other day in kind of this realm of logic, and I think the quote was, mathematicians aren't computer science. Like, we just care that it's possible that this will work at some point. We don't care if it takes a million years to do. So, like, efficiency isn't my main concern.
Chat's now
especially when we get to...
yeah, we're not going to get very efficient in a minute, are we? Chat suggested a way to disturb... people watching can see it on the screen underneath. A way to disturb every millionth person, so that you're really only affecting a few people.
The problem is, of course, well, we'll get into that later, but the problem is that you're still affecting the same amount of people. And that I'm going to get to in a second. I just don't want to get ahead of myself. Okay, now, a bus turns up. A tour bus rides up to the hotel and is like, hey, we have bookings. The receptionist is like, oh, I completely forgot about the bookings. The hotel's fully booked again. And looks at this tour bus, and the bus has one seat for every natural number. It's got, infinitely many seats. The same amount of seats as there are rooms. But obviously, all the rooms are booked up, and you can't do the same trick because there's not a finite number of people coming in wanting to have a room. So what do we do?
Right? Sorry, that's not obvious.
Yeah.
You can't do the same trick again. And maybe it's the people who mentioned inefficiency might feel like maybe we should give them a chance to argue that point. I got bored at 6 people on screen. Let's see what chat says. Oh my goodness. Someone in chat just says they can sleep on the bus. I guess that's the solution. Somebody before has told me that Hilbert should really quickly rush out and build a second floor of the hotel, which I quite
I might get to that, but I might not. That depends. That all depends on how far we get. Maybe I'll do another one where I talk about different floors. So but the receptionist does have a way to do this. Have people talking about this in chat? I don't know if I should just keep...
There's one really good suggestion. Oh, sorry, I may have got ahead of chat a little bit. Sorry, I do that sometimes. Chat's coming through now. Just a quick shout out to Bobby, who's doing a really good job in chat, moderating and putting things through, checking for YouTube music videos. Please don't rickroll Bobby. Right, okay. There's now a suggestion. Someone in chat has heard about super tasks, so I wonder if there's a video on this YouTube channel about tasks and super tasks. So if you've watched every video on this channel, then you've seen some sort of weird infinity machines. It's a really fun video, but I think not everyone's seen it. I always pause it because we can't do the trick from before, right? We can't just shuffle.
Because you can keep doing that, but you still have you every time you do the trick, you have one more person to put into a room, right? If you think about like two people coming into the hotel, the trick is that you do one at a time. You move everyone once, put that person in room one, move everyone again, put that person in room one. Um, but the problem is now you'll never run out of people to keep putting in room one, and so no matter how many people you put in, you still have infinitely many left. The trick at this point is to everyone who's already has a room, say someone's in room N, you ask them to move to room 2N. So the person in room 1 goes to 2, 2 goes to 4, 4 goes to 6. And just like that, everyone, even though the hotel was fully booked, you now got half of the rooms available. And so everyone on the bus moved to room 2N minus 1, where N was their seat number on the bus. And so they slot in perfectly. And just like that, you've got the hotel's fully booked and you've accommodated everyone. Weird things about infinity still. So again, this could work with any number of infinities, like any finite number of infinities. You could do the same thing, right? If you have two buses, then you move everyone. You've got like 3 infinities to fit in this hotel, but then you move everyone to 3 times their room number, and it fills in. The next question is, okay, what if you have infinitely many buses? So like say you have a train with infinitely many cars, and each car has infinitely many seats. And for people in chat who might know a little about this, when I'm using the word infinitely, I mean 1 seat per natural number. So this is a very specific distinction.
I'm now faced with the task of drawing an infinite number of buses on the screen.
They could get smaller and smaller.
I've got a trick. Smaller and smaller. Oh, I see. Like some
yeah,
sort of...
so they make it fit.
You're going to do like a geometric series on this.
Okay.
Mm.
Like, I don't know. I always think about like on a...
never have agreed to do the drawing.
The weird geometry where the closer you get to the edge, the smaller you become, and so you can fit. What is that? The hyperbolic plane or something? The disk?
Oh, now you're going.
That's different kind of maths. Different kind of maths. Maybe someone will come on and talk about non-Euclidean geometries. I could talk about the history.
So people in chat, if you want to just quickly address in chat, people have got very worried about the people on seat 1. Somebody's worried about the very first person, and I suppose I've only written a little bit on screen. I should maybe have been a bit more careful to say that we're sending the people in the hotel already to rooms 2, 4, 6, and then the people on the bus can go to rooms 1, 3, 5.
Yeah. So
I really regret drawing a bus driver. I drew a bus driver to make it look like a bus. They don't get a room. This is not the best drawing. What am I saying? This is the best drawing. You think you've seen other drawings? Other drawings are not.
I'm very glad you started drawing because I can't. So.
That's not a technical thing. I gave you access to the board and then fix on the pen.
It took me a while to sit and think about this. So without making anyone in chat figure this out for themselves, it is possible to fit this infinite train in the hotel. You essentially assign every person. You do the same thing again like you did with just the one bus of moving everyone in the hotel to room 2N. And now assign every car and every seat in the car a number. So say you're in car, so your car is C and your seat is F. So if you're in the 3rd car in the 5th seat, you have C equals 3, S equals 5. And then all you do is send that person to 3 to the C times 5 to the S.
Oh, you're hitting them with a solution that's... I always find it interesting which solution people pick. Tell me again, sorry. The bus number, which way around was it? So
you go to 3 to the power of the bus number, and then 5 to the power of the seat number.
Okay. Tell me. So this is bus number 1. What did you call that? B or C or something?
Well, I was talking about cars of trains, but if you've got buses, go B. So 3 to the B times 5 to the S.
Oh my goodness. Okay. Oh, sorry, that's why you said train.
Yeah, well, it doesn't matter. It's an analogy,
That's crazy.
And then, of course, what that gives is an odd number, and so they won't, because we've moved all the people already in the hotel to an even number, they'll just slot into free rooms. And due to uniqueness of factorization, which is a thing you prove at some point, blah, blah, blah. Basically, I'm not going to tell you why, because I don't know the proof off my head, but you'll never have that. That will never repeat. No, I guess it's just prime factorization is unique. I guess that's all you need. Yeah. I was thinking of a more complicated proof that doesn't. I'm getting ahead of myself.
That's crazy. Can we talk about ways that don't work for the lots of buses?
Well, what you might notice with this way is that we're still going to be left with empty rooms, which is very interesting, right? No one's being sent to room 7, for example. So like somehow we started with one infinity, we added infinitely many infinities, and we've got space left over.
Suggestions from chat, and there are questions on this one. This one, I think there's other YouTube videos, by the way, available out there. You know, you could be watching any of the YouTube videos out there, like
Probably.
like the Rick Astley one, for example. But you've chosen to be here watching this YouTube video. There are other YouTube videos out there that I think do a little bit of Hilbert's Hotel, and they usually stop before this bit. They usually stop just before here.
So I'll get to a different way of seeing this later. When we start talking about actual numbers and not buses and people and hotels.
There's a 5 to the... So suggestion in chat, which I think is very good, is why 3 and 5? Where have they come from?
3 and 5 because they're prime and because they're odd. Because they're prime, it means you'll never... Because if prime factorizations are unique, you'll never have one number which is 2 different ways of doing 3 to the b, 5 to the s. And so everyone's going to be sent to different rooms, and because they're odd, they won't go to the even rooms that the people in the hotel were already sent to. It could have been any other odd prime. I could have done 17 to the b, 31 to the s.
Somebody
3 and 5
in
were
chat
just the smallest
suggests,
ones I had available.
or use 5 to the b, 3 to the s.
Yeah, that would also work.
There's nothing actually
completely
special
fine.
about this. There's a sort of way to swap all the coaches.
But it's like, it feels weird because like in the other examples, we perfectly fit. We had like kind of a 1-to-1 correspondence, right? And now now it's empty. We still got empty rooms. It feels like somehow like we've gotten rid of spaces by adding infinitely many people, which feels weird. I am going to throw some history in there, but history about infinity, that's people have been talking about infinity in philosophy for a very long time, but maths not for long. If you go all the way back to Aristotle in like ancient Greece, he was kind of the first person to say, okay, infinity has no place in mathematics. He kind of had this distinction between potential infinity and actual infinity. If you're doing maths A level, you'll have like encountered infinity when you're talking about limits, and that's kind of this idea of like the potential infinity. Aristotle would be like, this is fine because you're not actually using an infinite number of things. You're like, you know, it's potentially infinite, the sequence that you're taking the limit of. But he said, you know, the actual infinity can never turn up. And this was echoed by Galileo, like the Galileo dropping the things off of the Leaning Tower of Pisa Galileo, who noticed these weird things with infinity. If we kind of move away from our hotel example, let's put that to the side for now. Just thinking about the natural numbers as a whole. What we've shown with the first bus example is that there's the same number of even numbers as there are numbers. Maybe I'll scroll back a bit. What do I mean by same number? I'm gonna talk about that for a second. There's kind of some like kind of elementary set theory in a way. When we say that it's the same number of 2 things, of like 2 sets, it means kind of we're putting them in a 1-to-1 correspondence. The way I was if you have 3 oranges and 3 apples, the way you know that there's the same number of oranges as there are apples is you can just pair them up 1-to-1. But this is what this idea of like a 1-to-1 correspondence is that you can like pair them. And so if you apply this idea of comparing size by corresponding 1-to-1 to infinite collections, everything falls apart, because then you get the evens, which are part of the natural numbers, being the same size as the natural numbers. And in our last example with the infinitely many buses, you know that there are less apples than oranges if after you pair everything up, you have oranges left over. But then what our thing just showed is that infinity times infinity plus infinity, whatever, is actually less than infinity. And we'd have to kind of show the other one to show it. So Galileo was like thinking about all this and just said you can't do this. It makes no sense to talk about this in mathematics. There's no sense. He also there's like a nice. Ooh, I might write something on the screen.
I'm over just
Um,
down and left a little bit.
yes. He also another thing he found apart from like the evens and the naturals, or even the primes and the naturals, you can pair those up one to one. You know, for each prime, not for each square number even. Sorry, I mean you could do it with primes, but for each square number, 1, 4, 9, 16, just match it to its square root, its positive square root, and then you get this one-to-one correspondence. He also noticed this with like geometry. If you have like a small line and a big line, Galileo noticed you can just if you like take like a diagonal
Ooh, can we talk?
like drawing, like if you do like this kind of array situation, every point on the small line would be sent to a point on the big line. And so again, you've got the same amount of points even though the line is bigger. Galileo concluded, no infinity in mathematics, this is it. And that was held for hundreds of years. Until the 1800s, until the late 1800s. I mean, technically Bolzano started defending it in like 1815, but no one listened to him. And he got a couple things wrong. In comes a couple mathematicians. The most notable one is called Georg Cantor. I'm actually writing a dissertation on him at the moment, so I know a lot about him. I'm not going to go into too much detail, but he was the first person to start introducing this idea that we can talk about infinity in math. And just, sure, you get weird things where this infinity plus infinity is equal to infinity, but that's not a problem. Let's just like accept that and see where we can go, right? This kind of mathematical, like, okay, this is weird. How can we push this? Where does it go? And he sends a letter to another mathematician, Dedekind, in the 1870s, asking, "Hey, like, do you think we could match up the natural numbers to the rational numbers? I think I found a way to do it." Because like all we've been talking about is like matching. We've been talking about so far. We have all the natural numbers, 0, 1, etc. Yes, 0 is a natural number. Don't at me. And we've been able to say it's the same size of like its infinite subsets, right? Like if you take infinitely many numbers out of the natural numbers, you still have the same amount of infinity. But what if you take what feels like a bigger infinity, but it's still infinity? Okay, so take the rational numbers. There's a lot of them. Feels like there's more rational numbers than whole numbers. But what Cantor did is he drew this little grid, which I will draw here. You can write all the natural numbers kind of in a grid. And over here you have 2 over 1, 3 over 1. That goes that way. Here's 2 over 2, 3 1. Oop. 2 over 3. Yep, I know how to do things. That's 3 over 2. That's 3 over 3. So if this goes on infinitely, you can convince yourself this includes every single rational number there exists, right? Because every rational number is just a fraction of two natural numbers. And then what Cantor did was like, okay, well, let's start here. Let's say that's 1. And then let's go here. Let's say that's 2, 3, 4, 5, 6. Ooh, and then 7, 8, 9. He found a way to find this one-to-one correspondence. So now we've proved there's the same number of rationals that there are natural numbers. And so now you might be thinking, okay, this is just infinity. Every collection of infinite things is going to be the same size. And this is a very natural like takeaway from everything I've said, because everything I've shown you so far, infinitely many things has, even though you think there might be more or less, there's the same number of them. But then what Cantor asked Dedekind was, okay, what about the real numbers?
Could we do the real numbers in a second? Sorry. Pause
okay,
really briefly
we can put that there,
and then we can. Chat's keeping up. They're doing really well. Somebody asked a history question. First off, thanks for the history. I don't think I told you earlier. History seemed quite popular. Somebody asked,
great.
What was the effect? Is it true that Cantor? Nobody really listened to Cantor, and Cantor went a bit mad. Is that Is that a part of the story, or is that something that Chat
So
said?
it's very like this has been kind of there was one like someone who wrote a biography of Cantor who like made up a bunch of things just for the sake of the story. Like you might have heard that Cantor was Jewish. He wasn't. He was actually very strongly Christian. Um, this guy made it up. He also made up like a lot of things, and
Not
so
that
there's a
there'd
lot
be
of weird
anything wrong with
information out
being
there.
Jewish, of course, but yeah.
No.
Um,
I so
yeah.
Cantor had opponents. People really didn't like that he was talking about infinities. They had this very like firm idea of what math should be. This guy Kronecker, you might have heard his name, he really didn't like irrationals even because the way irrationals were introduced was through infinities. We can talk about that maybe later. And Kronecker and Cantor really despised each other. I read a great letter that Cantor sent to a friend of his, being like, Cantor had applied for a university position in Berlin, which is where Kronecker was, and he didn't apply expecting to get it. He didn't apply wanting to get it. He just applied because he knew how angry it would make Kronecker. And in this letter, he writes, "If you are in Berlin, it will be as if you are in the plains of Africa with the lioness roars he lets out when he opens my like letter." It's just, like this really poetic. All letters between mathematicians back in the day are so poetic and so dramatic. It's so much fun to read. If I do a history one, I'll maybe like show you a couple. Um, but uh, Cantor had opponents, and these opponents had very powerful positions in like the big universities in Germany. However, and he had mental health difficulties near the end of his life. He had like also just general health difficulties. Um, it is not, but his ideas were by and large accepted by history. In like he was doing this maybe 1870 to 1890, like that kind of period, maybe late 1890s as well. Hilbert has a very famous quote. Hilbert, who was maybe the most famous mathematician of his time, um, where he says, no one will free us from the paradise that Cantor has created, or like no one will take us away from the paradise that Cantor has created." Like this paradise of set theory and infinite like that was kind of the idea that Hilbert had, and because Hilbert had it, a lot of other people had it too. Um, so his ideas were a lot more accepted than Bolzano's were 50 years before. Um, Even though he had his opponents, he did have places where he could publish his papers. Um, yeah, and with time, history chose Cantor over Kronecker.
You mentioned Hilbert back in there, sort of full loop background to Hilbert's
Yeah,
hotel.
Hilbert
Um,
Hilbert liked a lot of what Cantor did. I can very much see a lot of Hilbert's ideas as kind of an evolution of what Cantor was talking about.
just to acknowledge some things in chat about the buses again. I let a conversation run in chat about
Yes.
putting people on the buses that I thought Zakkai might like to hear about as well. People were discussing using other primes. Some
Hmm.
people are in favour of using much larger primes so that you get more space or more empty rooms. I think Kai asked about what's the one that gives you the most space, and I think chat talked it through and realised that you can always have more space whenever you think you've
Yeah.
got quite a
The thing
spacious
with
hotel.
more space though is that no matter what we've just shown, so like you can see our buses as a analogy for the rational numbers, kind of. That's what I was a bit sneaky. Our buses are the rational numbers. Our B and S. If you put B over S for every one, you got all the rational numbers. Like you can kind of see like the grid in how James has drawn it as well. And so like you still like no matter what, you still have the same amount of people, even though you've got empty spaces. That empty space kind of doesn't matter as much because you've got the same amount of people. The empty space was a big problem because you've got this idea of like, okay, well, with if we hadn't found that one-to-one correspondence that I found with my grid, and we just had this thing, we would have that the rationals was smaller than the natural numbers, and also we have that the naturals are smaller than the rationals because they're included in the rationals, obviously. The question of whether that means the rationals and the naturals are the same size just from those two facts feels like a very intuitive thing and something which is very true for um, finite numbers is very difficult to prove in infinity. You can prove it. I don't even think you need the axiom of choice, although you might. But it is provable. No, it is provable. Yes, it's called the Cantor-Bernstein or the Schroeder-Bernstein theorem. Actually, Dedekind proved it without publishing it months before anyone even published it, and just never told anyone.
Let's just not publish it. That's not a good play. Let's not
Yeah,
encourage this
he just
behaviour.
was like, "Oh, this is a cool thing I can manage to prove." I'm sure Cantor would like this, but he wasn't getting along with Cantor at that time, so he didn't send him the solution. Anyway, um,
Chat's also doing book recommendations. We've got a recommendation
oh
for The
yeah,
Man Who Loved Only Numbers for maths and philosophy.
hmm. I've not read that, but that sounds good. Um,
Somebody in chat's reminded me that I promised them I would tell a maths joke, and I'm going to do it at the end. So I just want Zach to
okay.
know that it's coming, but I'm not interrupting this presentation to do a maths joke. Sorry, Zach.
Um, um, yeah. So now we've got. Can I go back to the reels now? Am I
I
on?
will let you do the reels. Let's do the reels. Sorry for slowing you down, but I
No,
think
this
we
is
should
fine.
tell
No,
them
no,
about
no.
the reels.
Giving everyone time to like process, and you made me talk about you let me talk about histories, which I'm always happy to do.
Sidetrack.
The thing with the real numbers is that there are more real numbers than there are natural numbers, and we can prove this. So what that means is that there are more than one type of infinity, and so because of that, I'm going to do something which I've been wanting to do for a long time, but didn't want to get ahead of myself. I don't like when people use the like sideways infinity symbol when they're not talking about limits and potential infinities and stuff. Um, like this symbol, ooh, I can't even draw it. Um, it's confusing because it means infinity, but there's a lot of different types of infinity. There's a lot of infinite numbers. And so instead of that, I'm gonna introduce a little bit of notation to you, if I can find my pen. We call so what we call countable infinity, which is the size of the natural number, as we call it, because you can kind of count it. So like the cardinality of the natural numbers, we give that the name Aleph 0 or Aleph null. Aleph is the first letter of the Hebrew alphabet. It was introduced by Cantor as this because he was like, we ran out of letters. We've used all the Greek ones. We've used all the Roman ones. Let's do this. Let's do this instead. Um, and there are some like really interesting philosophical, just kind of like coincidences with the fact that he used Aleph because of some things to do with Judaism and the what Aleph kind of means in the alphabet, but I'm not going to get into that. This is what we call countable infinity. It is the smallest infinite number. What we can prove, and what I will prove if we have time, is that nope, that's the wrong one. Whoops, ignore that.
The hungry crocodile.
This is strictly smaller than the size of the real numbers.
Sorry, I opened a box over the top. There we
go. My reel with a bit.
I think it's really funny that you're writing. Well, not really funny, but it's slightly odd maybe that you're writing. So this n with a double line is the all of the natural numbers. It's the symbol for the set of all the natural numbers. And you've put mod signs around it to say the size of that. I mean, it's infinite.
Yes.
It's infinite.
Yeah, but we can still talk about it. We can still talk about the size of the set, right?
Using the same notation that you would for like the length of a vector or something. It's just like the size. Just trust me, the size. And it's got a name.
Because the length of a vector is the size of the vector. If you think about it, it's I think the notation might have come like when the notation for this was first introduced. It started like you could do it for any kind of sets, and then it boiled down to being like mods and like turning negative positives and things. Because like you can think about the size of -5 to be 5. You've got 5 things there, whether or not they're negative or not. Anyway, I'm gonna prove this now.
Should we prove this first? And then chat's asking amazing things, but I don't want to sidetrack you too much. Let's prove it. Let's do this.
I think we can prove it. Let's do this as a proof by contradiction, which is assume it's not true. Assume that this is equal. Let's assume I can't rub this out for some reason. Is my pen working?
Oh.
My pen has stopped working.
I can write just about. You're doing a Cantor. Yeah, we can do this.
Yeah, you can. Okay, if we assume it's not true, that means because the Aleph null is the smallest infinity, that means that there are countably many real numbers. And if there's countably many real numbers, we can put them in a list. So, R1, R2, R3, R4.
It's like putting them into the hotel, I guess, and then looking at the register for the hotel, who's in room 1, who's in room 2.
Yeah, exactly. Like if we had rearranged the hotel to fit every real number in there, because we're assuming we can, who's in room one, who's in room two. Um, I don't know. The whiteboard app has just stopped letting me
Sorry that
do
that's.
it. Okay, so let's write down our list.
Okay.
Let's start with R1. And let's just choose a number for it. Let's just to make it easier, put them all between 0 and 1.
Oh, okay.
So let's let's have it 0. Yeah, whatever. Okay, let's just say that's R1. Of course, if there's a different R1, we can always just swap them. So it doesn't matter what we put in what position. We're just talking about if we can put them all in a countable list. Let's do one for R2 as well. So maybe 0.88888888 continuously.
Okay,
no, you could do whatever you want. I mean, this is also helpful.
888 seems, yeah.
Yeah, let's just keep going 8. Why not?
Okay, yeah, we've got to put that reel. We're listing all the reels, so we've got to list that one at some point.
We're listing all the reels. That one's going to be at some point. Yeah.
I feel like we're taking turns as well, so that's nice. Okay,
go ahead, do your one.
A couple of weeks ago, I tried to list this number and I got it very accurate, except I got one of the digits wrong. So I've been practicing. LD.
Oh, my pen's working again.
Oh, your pen's back. All right. So we've got a list of real numbers.
Yes, and because we've assumed that we can write all of them like this, then we can, we have all of these. What we're now going to do is contradict ourselves, because we're doing a proof by contradiction. So I'm going to make a number which cannot be in this list, but is a real number. And it will make sense once I do this why this is called the diagonalization argument, or the diagonal argument for the difference. So I'm just going to circle this number, and then this number, and then this number, and imagine me just continuously circling all of these numbers. Mm-hmm. And then I'm going to make a number that makes sure that at every decimal point, its decimal point is different to the ones I've circled in red. So let's say it is always 9, or let's say it's always 8, unless the one in red is 8, in which case it's 1.
Okay, so you're building a new number.
That's an easy way to do it. We're building a new number.
let's write down.
Yeah, sure.
Okay.
So let's call this D. So let's start with 0 again. So this one's not an 8, so that's an 8. And then this one's an 8. That one's an 8. And then if this one wasn't an 8, we could put an 8 there. And that would go on ever. And it would be a real number. It's just 0 point and then a bunch of 8s and 1s next to each other. But because at every decimal point, it is not equal to one of the R ends in our list, it means it can't be in our list. We've made a real number that cannot be in our countable list. We're reaching a contradiction that we can't put all of the real numbers in a countable list. So there are strictly more real numbers.
This is crazy.
If you want to know exactly how many real numbers there are, and I'm going to say this without proof because the proof might take a hot sec, but I'll tell you right now. The size of the reals, the cardinality of the set of real numbers, is 2 to the aleph 0.
Ooh.
So think about that for a second, and that's a bit weird. Why is it 2 to the aleph 0? Well, you can make a one-to-one correspondence between the set of real numbers and the set of functions from the natural numbers to a set containing two things. That's how we define 2 to the whatever. And so I was saying a lot without explaining a lot of it. Don't worry if you don't understand it. There's a lot more in what I just said than I just said.
So the left-hand side of this equation is impossible to imagine because it's the number of real numbers that there are, which is huge, mind-bogglingly large. It's a number so big.
And the idea that the number of real numbers there are is 2 to the power of the number of natural numbers there are is so weird to think about.
Two incomprehensible things they're incomprehensible in different ways, I think. The claim is that they're equal to each other. So.
Cantor managed to prove that these two, that there were more reals than naturals. He didn't initially prove 2 to the aleph 0, that came later, but he proved there were more real numbers than naturals. And so the very natural next thing to ask is, okay, were all there more? And yes, you can mimic what I've done with the real numbers and make that into a very almost identical proof that proves that, okay, some elementary set theory, if you have a set of elements, the power set of that is the set of all of the subsets. So if you have a set containing 1 and 2, then the subsets of that set are the empty set, the set containing nothing, the set containing one, the set containing two, and then the set containing one and two. And so the power set of the set containing one and two would be the set of all of the things I just said. You can mimic my diagonal argument for the real numbers to be a diagonal argument that shows whatever you start with, the power set of what you start with will have a bigger number. And so the power set of the real numbers, the set of all combinations of real numbers, is strictly bigger. And that's actually, again, 2 to the 2 to the Aleph 0. Taking the power set is taking 2 to the part, whatever you just had. So there are infinitely many infinite numbers. Right. The question is, do we miss any? Cantor's question, when he had just the two, when he just had the natural numbers and the real numbers, are there any infinities in between, or is 2 to the Aleph 0 the next infinity? Is it Aleph 1? So
somebody
kind of question mark equal sign.
Aleph 1, yeah.
Proof not included.
I guess we haven't said what. I don't have any idea what Aleph 1 is, I'm afraid. So
Aleph 1 is just what I'm using as the next biggest infinity after Aleph 0. You start with Aleph 0, you get to Aleph 1. Whatever. You're just numbering the infinities.
It's a rather ambitious
plan.
This
is called... the idea that 2 to the Aleph 0 is Aleph 1 is called the continuum hypothesis, because people would talk about the real numbers as a continuum, right? The real line is continuous. And so that's why it's called the continuum hypothesis. It's to do with the continuum. Whether or not the size of the reals is the next biggest infinity has now been proved unprovable from the axioms we use now. Hilbert has a
whenever
really
I say
famous...
that something is too pure, I'm joking a little bit.
Hilbert had a really, really famous speech at the 1900 International Congress of Mathematics, where he listed out 23 open problems. And he was like, these are the biggest problems in maths. We have to solve them. This was to the end that he had a program where he was trying to make something to prove every single mathematical statement. That didn't end up working because of Gödel's incompleteness theorems. Anyway, the very first problem on that list of 23 problems was finding a proof for the continuum hypothesis. 30 years later, Gödel proved that it is possible that the continuum hypothesis is true. And then in the 1960s, someone called Cohen proved that it's also possible that the continuum hypothesis is false. And so it's not provable from what we have. It's completely independent from the axioms we use for most of mathematics. Sure, you could add more axioms that might change that, but yeah.
As the applied mathematician on stream, let me back you up a tiny bit. I kind of accept this.
Your audio has gone really, really weird for me. You kind of sound robotic, and I'm not sure if that's just a me thing.
1 2 1 2. Bit terrible. Sorry, everyone. Sorry if the audio is bad at home as well. I'm going to talk anyway and let chat tell me that I'm bad. I kind of accept your diagonal argument to say that if you try to list the real numbers, that's a fool's errand. There'll be one that you missed out, or maybe others that you missed out as well.
Okay, now you're still robotic and quieter, so I...
Oh no, sorry. I think I'm fine on stream. I think I'm okay, so I'm just going to keep talking.
Okay, it might just be... Maybe I'll try changing my output.
Okay, I accept this argument about diagonals to say that there's... you can't list them, or you can't number the real numbers. That would be mad anyway, really, if you could just assign a whole number to all the real numbers. It kind of feels to me like there's way more real numbers, and in fact that's true. I accept that there's a question for, okay, it's bigger, is it the next one, or is there anything in between? But then there's two levels of weirdness, I think. Two levels of weirdness. One, that we don't know. We haven't done that question. We can't say, oh yeah, there is, or no, there isn't. We haven't done it yet. And then the second level of weirdness for me is that we will never prove it, and we've proved that. The sort of meta question of, will we ever prove the continuum hypothesis, something in between the size of the reals and the counting numbers?
If I'm allowed to start talking about philosophy for a second, philosophy of maths at least, there is a current thing called multiverse theory amongst the philosophers of set theorists. And so basically the question whether are there more infinities in between? Well, what do you mean by that? Is it true that there are more infinities in between? Well, maybe, but true according to what? The multiverse theory says that there are there's universes of sets where there are infinite sets that are between the sizes of the naturals and the reals. There are other multiverses where there aren't. So there's universes where the continuum hypothesis is true and universes where they're not. There are people really oppose this, and people are like, no, there must be a fixed answer. But this is a kind of up and coming thing, which I kind of agree with. But it's a very thing, like in mathematical logic and kind of philosophy of maths, you get this idea of what does truth mean? Does truth mean provability? Well, actually, no. But like truth always means true in some kind of model, like true according to a structure, right? In the natural numbers, it's true that there aren't any numbers between 1 and 2. But in the real numbers, that's completely false. There's actually more numbers between 1 and 2 than there are natural numbers. And so truth is relative. So you like when you get to kind of where I am in studying pure math, in like studying set theory and logic and mathematical logic, you have to be really worried about what you mean when you say something is true or not. Because obviously, when you're talking about applied mathematics, that's just, does it apply to our universe? Like, does it apply to the world around us? In which case it's true, otherwise it's not. Sure, I can see how that's more helpful for the world and has applications, whatever. I think this is really interesting, and that's why I study it. But the idea that there's, first of all, different sizes of infinity, mind-boggling. And this is actually proved very helpful in real life applications. A lot of computer science rests on things that set theory has come up with. There's a whole other thing called ordinal numbers, which I don't have time to get into. But you can do kind of recursion and things when you're dealing with infinite things. So if a computer science has a program that's going to go infinite, like go on forever and then stop, if it like keeps looping back on itself, the question of how many times it does that changes if you're talking about like L of 0 many times, 2 to the L of 0 many times, and that can really change computability. I think this is really stretching the bounds of my knowledge because like that's getting too applied for me. But I know this stuff has its uses. I don't care about those uses personally. But if you're like looking at this and being like, oh, coming from an applied mathematics point of view, like why do you care? I mean, if we do a history episode, I'll talk all about that issue. But
that's getting engagement. That's how you get the clicks. If we get Zakkai back on the stream, we can talk about history of maths for a whole hour, and we'll see that. That's been popular in chat when it's been mentioned before. We're getting close to 6 o'clock, so I think it's time to wrap up a little bit. Somebody says, how come nobody's abusing chat? Chat is highly moderated. Thank you, Bobby, who is a current student who has been not doing any fun Infinity stuff and has just been moderating chat. Also, we have the best chat around here. We have the nicest people in chat who are just really nice and want to talk about maths. Someone says, thanks, Zakkai, in there. They say that they met you on an event once. You helped teach them some maths on AMSP, and now they've just got a maths offer. So they're very excited by that.
Awesome.
So hey, you met a person, and now we're here on the internet, isn't that? That sounded weird when I said it out loud.
I'm sure it was very nice to meet you and teach you math.
I'm going to it's all anonymous, so they've no idea. This could be anyone. I'm going to let chat catch up a little bit. There's a bit of chat lag, and I think the time has unfortunately come for me to do my maths joke. Are you ready for a maths joke?
Very.
It's slightly statistics themed, although I'm afraid that is revealing the punchline. And I don't think I've picked the right mathematician to try it on. So a really prominent maths person I met, up and coming, very exciting. I'm following their career with interest. Told me the following maths joke. So I start all my jokes. Following joke, : what do you use to predict underwater crime rates? And the answer is Poisson PD.
Because fish.
Because Poisson like fish, and also PD like police department or probability distribution. Yes, that's right, I have. Explaining the joke helps people understand the joke. That's how it's a good maths educational live stream. You don't get that on all live streams. Zakkai, thank you very much for being on the stream. Bobby in chat, thanks for moderating. People want to send in philosophy of maths questions. If they email the Maths Club email on screen, do you think between us we can field maths and philosophy questions, maybe? We haven't discussed this before. if you email things to the email address on screen, we can't stop you. Emailing questions to those will make it to the University of Oxford, and after that, maybe be seen by someone at some point. People were not keen on the Poisson PD joke. Good. Okay, I think we're going to wrap up in a second. Somebody in chat has promised to tell this joke to everyone else they know, so Zach at Woodhouse will be very pleased with that one. And
if you're interested in philosophy of maths, the person who lectured me in philosophy of maths published his lectures as a book.
Ooh.
So I think you can find those. It's just called Lectures in the Philosophy of Mathematics by Joel David Hampkins.
I'm going to really quickly look it up, because that seems
If
like
that's something you're
I can
interested
do. Joel David Hampkins.
Yeah.
We may put a link in the further reading. If I do further reading, lectures, and the lecture notes are just out there. Or it is a book that you get. Oh, it's a book that you can acquire. Oh, it's got a snazzy cover. Google's given me one of those buttons for get book.
I don't know if you're asking me a question.
I'm always looking out for cheap copies. I can see a copy for about 17, 18 quid on some services. Okay, good. I need to be really careful not to put my emails on screen. Okay, before something goes terribly wrong with the stream, thank you once again to Zakkai for coming on the show. Thank you to Chat for being here.
Yeah,
Bobby for moderating. The researcher this week was Zakkai, and we're going to finish by looking at the Promise advert again, because I'm so pleased that I remembered to show it to people. Oh, it's gone. It's gone. It's really gone. Okay, we're not going to finish by looking at the Promise advert. I have once again failed to show it to people. Apply for Promise, people, or at least have a look at the questions. Even if you're not eligible for Promise because you're too old or too young or too much in a university right now or not interested in doing a whole summer school, they've set some questions for people to look at on their website, and it's free. It's especially free to look at the questions. Right, cool. Take care, everyone. See you around. We'll be back in 167 hours for another episode of the Oxford Online Maths Club. Bye.